Hi, myself Sudheer Kurup. I work with Dr. Groysman in Chemistry Department at Wayne State University.
Hi, I'm Duleeka Wannipurage. I'm fourth year graduate student from Groysman Lab at Wayne State University. Today we are going to talk about the paper we recently got published in Chemical Communication about our newly synthesized chelating iron 2 bis alkoxide complex and its reactivity towards azoarine synthesis. Azoarenes are highly colored chemical compounds which can be used in different chemical industries as drug delivery agent, chemical indicators, textile dyes, and there are many other applications. Azoarine can be synthesized using different synthetic pathways, but that pathways require toxic starting material like lead salt, potassium dichromate, Carose acid, and it will produce so many byproducts. They are very toxic. So to prevent that, we can shift to transition metal mediated azoarine synthesis. That is not very common. We can see few examples in the literature. Here we have to react transition metal complex with azide to synthesize azoarine. First of all, azide is reductively split to give metal imido and dinitrogen as the only byproduct. After that metal imidose coupling to give azoarine.
Our lab has previously synthesized two monodentate iron alkoxides, but we faced issues with these alkoxides because the first generation alkoxide showed reactivity with bulky azides like acetyl azide, but it formed iron trist amido and iron trist alkoxides with less bulky azides. So to overcome this limitation, we designed a second generation monodentate alkoxide which improved the scope of the reaction, but it still showed poor reactivity with less bulky azides. To overcome this problem with the monodentate alkoxide complexes like disproportionation and also poor reactivity with less bulky azides, we designed a chelating ligand system where two alkoxide linkers are attached to the central phenyl ring. And the paper that we recently published, it can be divided into three sections roughly, where we talk about the synthesis of the ligand and the synthesis of the complex, and then Duleeka will talk about the catalytic aspect of the complex. So the first step is the synthesis of a terphenyl linker. The first step is a palladium catalysis decoupling reaction between 2-bromoboronic acid and 1,4-diridobenzene. So this will form the terphenyl ring, which is para-substituted with bromine group. This terphenyl is then reacted with tertiary butyl lithium, followed by reaction with benzophenol. We then react this ligand with iron plus silyl amide to form the complex. We crystallize it and then we use it for catalytic reaction.
So after we synthesize the complex, we focus to do catalytic reactions with different substituted azides. So here we reacted our iron complex with different substituted azide in benzene solution at 60 degrees centigrade. So we observed the different reactivity for this catalyst than our previous alkoxide complexes. We observed higher reactivity for phenyl azide, and also we got higher reactivity for para-substituted azide, and we didn't observe any reactivity for ortho-substituted azide. So if you're interested about our paper, you can read the paper. The link is in the description.